All right, in this video, we're discussing the sampling distribution for the sample mean. So what we're going to do here is basically initially sample from a normal distribution. So we're saying, hey, we have a normal distribution here with a mean of 16 and a standard deviation of 5. What would happen if I took, say, let's just illustrate this with a sample of 2, right? So I take a sample of 2 values, right? Another sample of 2, right? So on and so forth. So 2 values, and then what's happening here on the curve below is this is the average of these 2 values, right? So the average is what's falling down on the number line. Let's do it again. There's 2 values, see how the average ends up here, right? So we do that over and over again. We're trying to figure out what would happen if we plotted all these sample means from all the different samples of 2 we could get. Well, obviously we can't take all of them, right? We would run out of time because it would be forever and ever and ever. But what would happen if I look at 100,000 of them, right? So when you look at it, you see that there's a bell-shaped curve, right? Bell-shaped curve, even for just a sample of 2. So that's pretty interesting, right? So the parent curve here in gray was bell-shaped. The curve for the sample means, right? If you created millions and millions of sample means from different samples of 2 values from the parent curve, right? You end up getting a curve that is bell-shaped. All right, what would happen if I change the sample size? What happens if I change the sample size to, say, 16, right? Again, you can animate that. There's the average, right? What if I did 100,000 of them? 100,000 means here produces a bell curve again, but see how it's much more sucked in towards the center? It's less varied or less spread out. If you look at the standard deviation, it was 5, and here it's 1.25, a fourth of what it was here. The reason why it's a fourth is because it turns out that the spread in this curve for x bar will basically be the standard deviation that we started with divided by the square root of the sample size. So the square root of 16 is 4, so basically we get a fourth as much variation. Of course, if you did a sample of 25, it'll be even more clustered in, and then look at the standard deviation. It was 5 for the original curve. Now it's 5 divided by the square root of 25, or 5 divided by 5, and you get 1, right? Another thing we want to notice that for each of these examples, the curve was centered in the same location. The mean remains 16, basically, for each case. And that's because what's happening here is that the mean for the sample means is in the same place as the mean for the original curve in gray. So if you wanted to know what this population mean was, when the sample size were only 2, right? We had a bell-shaped curve, and each one of these little x bars was trying to estimate the population mean. Sometimes they were pretty far away from the center where the true population mean was. But as we increase the sample size, right, the curve kind of sucks in, and all our sample estimates, all our x bars, get closer and closer to that center, and that center is the thing we want to know, the population mean. So that's really nice. But so far what we've seen is that x bar follows a bell-shaped distribution, at least when the parent curve is bell-shaped, right? What would happen if it wasn't bell-shaped, right? What happens if the curve is uniform? Well, again, if I animate just a sample of 2, there's a mean for that. Another sample of 2, there's the mean, another sample of 2, right? What happens if I did 100,000 of them? It's kind of like a pyramid, right? A pyramid. It's not bell-shaped. But what happens as the sample size increases? What happens if it's 16? That looks a lot more bell-shaped, right? And when you get to 25, that's pretty bell-shaped, right? You could put a bell-shaped curve over the top of this. In fact, we can do that. Boom. Looks like a nice fit, right? So it's pretty bell-shaped at that point. And look at the mean again. It's basically at 16 again. So again, the mean for the blue curve, the curve for x bar, the mean remains the same as the population above's mean, right? So the mean for x bar is the population mean. The standard deviation, again, looks to be related by that factor of a square root of n, right? So it looks like it was 9.5, divide 9.5 by the square root of 25, which is 5, and you get a number that's pretty close to 1.91. So there it is. Okay. So this curve was symmetric and the bell curve was symmetric, and we saw that the curve for the x bars in both cases was a bell-shaped curve, but maybe that's just because that's what happens when the curves are symmetric. What if the curve isn't symmetric? What if it was highly skewed? Here's a very right-skewed distribution. So let's try with n equals 25, fit 100,000 of them again. Once again, we get a bell-shaped curve. Probably not if we had a sample size of just 2, right? If we had 100,000 and a sample size of 2, bell-shaped curve doesn't fit so nicely. See how it doesn't line up? Well, this still looks right skewed at a sample size of 2. But once you get a larger sample size going, then wow, the bell curve fits pretty well, right? Approximately, right? It's not perfect. You can see it's still a little off, right? It seems a little bit skewed to the right, but remember the sample size is still only 25 here. That's pretty modest sample size actually, right? So, but look at the mean again. Same property for the mean. The mean is 8.08 here. The mean for the blue curve, 8.08. Standard deviation, 6.22. If our sample size is 25, remember that would be divided by the square root of 5, and it gives us a standard deviation of basically 1.25. So very close to what it would be, right? Of course, if you could do this over and over and over again, it would be exactly a fifth, right, of this standard deviation, right? If you could literally do not just 100,000 samples, but all the conceivable samples that are possible, right? All right, so that's pretty interesting, right? So 3 different cases, right? Whether it was normal, whether it was uniform initially, whether it was skewed, the distribution of the sample means was bell-shaped in every case. The mean seemed to stay in the same location. In other words, the population mean was the same for both curves always. And then the standard deviation was always reduced by a factor of the square root of n, right? Now, even if we drew a crazy custom curve, right? Something that, you just made up in your head, something that's highly irregular, right? Like that. Let's try that. 100,000 samples of 25. Still looks kind of bell-shaped. The mean here, 22.49, the mean 22.49, right? Standard deviation, again, in that ballpark of 1/5, right? And look at that. Not a perfect bell curve because this is so irregular, right? And the sample size is only 25, but it's approximately normal. So what we can take from this is that the sampling distribution for the sample mean, in other words, what can we say about the blue curve? We got to think of 3 questions. What was its shape? Well, typically it was bell-shaped, right? Basically bell-shaped. What was its mean? It was always the same as the parent curve's population. So its mean was the population mean. And then what was the standard deviation? It was basically the standard deviation for the parent curve divided by the square root of the sample size. And that's essentially what we can take from this applet. All right, so a key thing to remember again is that the mean and standard deviation of the sample mean, the mu for x bar, and there's a mean for x bar, is the population mean, and the standard deviation for x bar, which is also called the standard error, so sigma for x bar is equal to the sigma divided by the square root of n. And of course, this assumes that the original population, x, had a mean of mu and a standard deviation of sigma, right? So if x has a mean of mu, the mean for x bar will be mu. If it has a standard deviation sigma, then the standard deviation for x bar, or the standard error for x bar, will be sigma divided by the square root of n.